pH calculations. Now, before we discuss pH calculations, we're going to talk about acids and bases and just review those definitions quickly. So, the first commonly accepted definitions of acids and bases were the Arrhenius definitions. And Arrhenius defined acids as substances that produce hydrogen ions when they dissociate in an aqueous solution. And bases will dissociate to produce hydroxide. So, remember what dissociation is. When a ionic compound is in water, the ionic compound, when it dissociates, breaks apart into its positive and negative components, its ions. And so any substance that has the hydrogen as its positive ion is an acid, and any substance that has the hydroxide ion as its anion, its negative ion, is a base. So for example, if we had hydrochloric acid, when hydrochloric acid dissociates in water, it breaks apart into the positive hydrogen ion and the negative chloride ion. And so that's what gives it the acidity. For sodium hydroxide, when it dissociates, it forms the positive sodium ion and the negative hydroxide ion. And the presence of that negative hydroxide ion is going to give it basic properties. But not all substances have hydroxide that are bases. So there are some problems with the Arrhenius definitions. Bronsted and Lowry decided to study this, and they came up with a separate set of definitions. So in the Bronsted-Lowry definition, anything that donates or loses a proton during a chemical reaction is going to be an acid, and anything that accepts or gains a proton during a chemical reaction is a base. Now, a proton is simply a hydrogen ion. The hydrogen atom is just a proton and an electron, and when it forms the ion by losing the electron, it's just a proton. So anytime you see something gain or lose a hydrogen ion throughout the course of a chemical reaction, it is acting as either a Bronsted-Lowry acid or a Bronsted-Lowry base, depending on whether it lost or donated the proton, or accepted or gained the proton. And so here would be an example. We would have to show hydrochloric acid in water, and what happens is the hydrochloric acid donates the proton to water. So hydrochloric acid, because it's losing that proton, losing that hydrogen to form the chloride ion, is acting as the Bronsted-Lowry acid. And water, because it's going from H2O to H3O and accepting a proton, is acting as the Bronsted-Lowry base. Okay, so pH is a scale, and it's used to measure the acidity of a solution. pH stands for the power of hydrogen. So anytime the hydrogen ion concentration is greater than the hydroxide ion concentration in a solution, the substance is going to be acidic. Anytime the hydrogen ion concentration is equal to the hydroxide ion concentration, it's a neutral substance. And anytime the hydrogen ion concentration is less than the hydroxide ion concentration, then we have a basic solution. And here's a pretty pH scale, so you guys can see how this works. Now the pH scale is within boundaries. So the pH scale ranges from 0 to 14. Even if you calculate a pH greater than 14, you would only report 14 as the answer. Similarly, if you ever calculate a pH that's negative, you would just report 0 as the answer. The pH scale goes from 0 to 14, no numbers outside of that range. Notice that in the middle of the pH scale is the number 7, and that represents a neutral solution. So anything with a pH of 7 is going to be neutral. Anything with a pH less than 7 is acidic, and anything with a pH greater than 7 is basic or alkaline. Many of the bases contain alkali or alkaline earth metals, and so that's why we call these alkaline substances. So pH is based on the power, aka the exponent, of the hydrogen ion concentration. And remember that we measure concentration by calculating the molarity of a substance. So to calculate pH, we are going to take the negative logarithm of the hydrogen ion concentration. Now don't be scared about that. The logarithm is simply a button on your calculator. So when you're doing these calculations, if you have the concentration of the acid, all you're going to do in your calculator is hit the negative button, hit the log button, and then type in the molarity of the acid that's given to you. Once you hit enter, that will calculate the pH of that substance. And remember that acids are the ones that are producing or donating hydrogen ions. And so we're going to use the concentration of acids to do pH calculations. So for example, let's say that I had to calculate the pH of a 0.05 molar solution of hydrochloric acid. So since hydrochloric acid produces hydrogen ions in a solution, I'm going to assume that the concentration that's given to me is the same as the concentration of hydrogen. So I can just take that concentration and plug it into the formula for pH. So pH is the negative logarithm of the hydrogen ion concentration. And so that's going to be the negative logarithm of the value 0.05. And once you hit enter in the calculator, you get a value of 1.3. So that would be the pH. Now, normality is a little bit different, and we're not actually going to use normality when we do pH calculations, but it is going to be important later whenever we start talking about mixing acids and bases together. So normality is where we adjust the molarity of an acid based on the number of hydrogen ions that are present in the formula. So it's really easy. You just take the molarity of the acid and multiply it by the number of hydrogen ions that would dissociate from that acid in its chemical formula. So for example, if I wanted to find the normality of 0.05 molar sulfuric acid, and I look at that formula carefully, I see that it actually has 2 hydrogen ions on it. So we call that a diprotic acid because it has 2 protons attached to its formula. If it was something like H3PO4, we would call that triprotic. So anything that has more than 1 hydrogen ion that would be the positive ion once it dissociates, that's going to be what we call a polyprotic acid. And you want to be able to find the normality of that. So to find the normality of this one, it's pretty simple. We're going to take that molarity, 0.05, and multiply it by the 2 protons that are present in that chemical formula. And so if I take that 0.05 molarity and multiply it by 2, I get 0.01. So the normality of that solution of sulfuric acid would be 0.1. Okay, so how can concentration be used to calculate pH? Actually, what we're going to do is we're going to take the pH and work backwards towards concentration. So if I know the pH of a solution and I want to work back to the molarity or the concentration of that solution, what I could do is the opposite of the logarithm. So the opposite of a logarithm is base 10. So if I take the base 10 and put it to the power of negative and then enter in the pH value that I'm given, that's going to equal the hydrogen concentration, aka the molarity of the acid. So here's an example problem. You can see that it's really not going to be complicated. If we have to calculate the molarity of a sample of hydrochloric acid and we're given the pH, all I'm going to do is take base 10 and put it to the power of negative and then that pH value, 2.9, and hit enter in the calculator. And then the value that's given to me is the concentration of the acid. So that value that the calculator will give you is 0.0013. And so that would be the molarity of that acid. We also have to think about something called pOH. And pOH is used to measure the basicity of a solution. So it's kind of like pH for acids, except that this is for bases. It's based on, again, the power of the hydroxide ion concentration. Now, it works the same way. Anytime you have a greater amount of hydrogen ions in a solution than hydroxide, it's going to be an acidic solution. Anytime they're equal, it's neutral. And anytime you have a greater amount of hydroxide, then you have a basic solution. Here we can see the pH and the pOH scales together. Notice that as the pH scale increases, the pOH scale decreases. So pOH works almost like pH, but backwards. So pOH is based on that power or exponent of the hydroxide ion concentration. And it's calculated virtually the same way, except using a hydroxide ion concentration instead of a hydrogen ion concentration. So pOH is equal to the negative logarithm of the hydroxide ion concentration in the solution. Remember that it's bases that dissociate to produce hydroxide, so you're often going to use this for bases. So for example, let's say I had to calculate the pOH of a 0.05 molar solution of calcium hydroxide. Now we really have to be careful with the bases because some of the bases contain 2 or more hydroxides that will dissociate. And so since this calcium hydroxide contains 2 hydroxide ions that dissociate, we have to multiply the concentration of that base times 2 because every time a calcium hydroxide dissociates, it's going to double the amount of hydroxide in the water. So if I take the concentration of that calcium hydroxide and multiply it by 2, The real concentration of hydroxide ions in this solution is 0.1. And if we plug that into the formula for pOH, I end up taking the negative logarithm of 0.1, and that's equal to 1. Okay, so if we know the pOH of a solution, we can work backwards to the concentration. And again, we use base 10 to do this because the opposite of logarithm is base 10. So the hydroxide ion concentration of a solution is going to be equal to 10 to the power of negative pOH. So again, here is an example problem. If we needed to calculate the molarity of a sample of sodium hydroxide with a pOH of 2.9, then I would do base 10 negative 2.9. And the answer again is going to be 0.0013. So the concentration of that sodium hydroxide is going to be 0.0013. So what's the relationship between pH and pOH? Well, in pure water, water molecules will actually ionize themselves and produce hydrogen and hydroxide. There's two different ways to look at this reaction that occurs in pure water. First, we can just think about the Arrhenius definitions. If that water molecule splits apart, it's going to form a positive hydrogen and a negative hydroxide. So when it dissociates or ionizes, it's going to break apart into a positive hydrogen and a negative hydroxide. Because water is able to form both a positive hydrogen and a negative hydroxide, because it has both the acid and the base components, according to the Arrhenius definition, it's what we call amphoteric. So kind of like an amphibian lives on both land and water, something that's amphoteric can act as both an acid or a base. The other way to look at this reaction is to think about the Bronsted-Lowry definitions. If I have two water molecules in contact and one of them transfers a proton to the other, I see that one of the waters lost a hydrogen, forming the hydroxide ion, and the other water gained a hydrogen, forming H3O+. So the concentrations of H plus and OH minus are going to be equal in pure water. And by the way, guys, if you see H3O plus in something, it's the same thing as H plus. It's that extra hydrogen ion that's in the solution. Usually in Arrhenius reactions, you just see the hydrogen ion, and in the Bronsted-Lowry reactions, you see the H3O plus. And that H3O plus is called hydronium. So it actually has its own name. H3O plus is known as hydronium. But either way you look at the reaction, the acid and base components are equal in pure water. For every water that ionizes, I get an acid part and a base part, and so those parts are equal. And in pure water, the concentration of each of those components is equal to 1 times 10 to the negative 7th. That's the molarity of the acidic hydrogen and the basic hydroxide in pure water. Kw is a mathematical constant that we use, and it's the product of the hydrogen ion concentration and the hydroxide ion concentration. So mathematically, Kw is found by multiplying the molarity of H plus times the molarity of OH minus. And so if we do that for pure water and both of those numbers are the same, we end up with 1 times 10 to the negative 14th. So that is a constant value at 25 degrees Celsius. Kw is going to be equal to 1 times 10 to the negative 14th power. Now, if we go ahead and negative log that equation, if I take the Kw and negative log it, and then on the other side of the equation, negative log the hydrogen ion concentration and hydroxide ion concentrations, remember that they were multiplied before, but once we use logarithms, we're now going to have to add those values. Then I would be adding the negative logarithm of hydrogen and the negative logarithm of hydroxide. And guys, those formulas should look pretty familiar because the negative log of hydrogen is the formula for pH, and the negative log of hydroxide concentration is the formula for pOH. So another way to look at this is that the negative logarithm of 1 times 10 to the negative 14th is equal to those two. The negative log of 1 times 10 to the negative 14th would be 14, and that's going to be equal to my pH plus my pOH. So again, just remember that hydrogen greater than hydroxide means that it's an acidic substance. Hydrogen equal to hydroxide means that it's neutral. And hydrogen less than hydroxide means that it's basic. So as one increases, typically the other decreases. If you have an acidic solution, it's going to have a greater amount of hydrogen and a lesser amount of hydroxide. Similarly, if you have a basic substance, it's going to have a lot of hydroxide and very little hydrogen. Now, again, we know that the relationship between those two things is that Kw is the product of those two concentrations. And since Kw is always 1 times 10 to the negative 14th at room temperature, if I know one of those concentrations, I can use Kw to find the other. We can take Kw and divide it by the hydroxide ion concentration to find the hydrogen ion concentration. Or we can take Kw and divide it by the hydrogen ion concentration to find the hydroxide concentration. All we're doing is some basic algebra to rearrange this formula. If I take Kw and divide it by the value I know, I can solve for the unknown value. So anytime I have a hydrogen ion concentration, but I'm looking for a hydroxide ion concentration or vice versa, I take Kw, divide it by the one I've got, and it'll equal the one I need. And here's just a little visual so you can kind of see how things come together. So notice that when I have a hydrogen ion concentration that's high, I have a very low pH. And then also at the same time, I would have a very low concentration of hydroxide and a very high pOH. And notice how those numbers change as we move down the chart. So at the top, that would be the most acidic substance, and it would be red if we use something like universal indicator to indicate the pH. As we move down and it becomes increasingly basic, notice that the hydrogen ion concentration decreases. You'll see that those hydrogen ion concentrations are increasing by a negative exponent, and the more negative that exponent is, it's actually smaller and smaller. So way down at the bottom, the hydrogen ion concentration is 10 to the power of negative 14. So that is a decimal point, 13 zeros, and a 1. So that's a very, very, very small number. And notice that that gives me a very high pH. At the same time, my hydroxide ion concentration would be pretty big. It would be 10 to the power of 0, and so that would be 1. So that would be the highest value on this chart. And the pOH for that value would be 0. So I hope that this kind of helps introduce the pH and pOH calculations. I know that there's sort of a lot of formulas. So this is kind of a very helpful visual to help you guys figure out how to do these calculations. Notice how it works. We can convert from one thing to any other thing when we have a concentration of acid or base, or if we have a pH or a pOH. Anytime I have one of those values, I could figure out any of these other values. So for example, if I had a hydrogen ion concentration and I wanted to convert that to a hydroxide ion concentration, I needed to solve for hydroxide ion concentration. Then in this direction, it tells me to take Kw, 1 times 10 to the negative 14th, and divide it by that hydrogen ion concentration I've got, and that will get me to hydroxide ion concentration. Same thing down here. If I had hydroxide ion concentration, but I wanted to move to hydrogen ion concentration, I would take Kw and divide it by the hydroxide I have, and that would give me the hydrogen ion concentration I need. If I have hydrogen ion concentration and I want pH, then it tells me that in this direction, if I have hydrogen and I need to get to pH, I need to do the negative logarithm of that hydrogen concentration I have. If I'm going the opposite direction and I already have pH and I need to get back to hydrogen concentration or acid molarity, then I would take base 10 and put it to the power of negative pH. Let's say that I had hydrogen ion concentration, but I needed to get over here to pOH. Well, then I'd have to do two things mathematically. I'd have to take 2 steps at least to get that direction in this visual. So if I had hydrogen ion concentration, I know that I can negative log it to get pH. And then what I can do is I can go from pH to pOH by subtracting from 14. So 14 minus the pH I have would give me the pOH I need. We could go from pOH to pH by doing the same thing. We can take 14 and subtract the pOH to get back to pH if that was what we needed to do. And notice that for bases, we can do the same thing here. This works for acid, so when you have a substance that's an acid and it contains hydrogen, you're starting here. And when you negative log that value, you've got pH. Well, if you're given a molarity of a basic substance, then you're starting here. You're starting at the hydroxide ion concentration. When you negative log that value, you'll be calculating pOH because you are negative logging the concentration of hydroxide because it's a base. If you already have the pOH, then when you take base 10 and put it to the power of that pOH you're given, that will get you back to the concentration of base, to the concentration of hydroxide. So really, these calculations are not complicated. What's complicated is looking at the chemical formula and thinking about whether you have an acid or a base. If you have an acid, then you're starting over here on this side of this visual. You're starting with the hydrogen stuff because acids have hydrogen. If you've got a basic substance that contains hydroxide, then you're starting over here. And so you need to really think about the formula you're given and think about the point you're starting at within this visual. And then think about mathematically how you're going to get from one place to the other. I hope that helped.